So welcome everyone to today's seminar. Today we have Tuilia Zillioto, who's going to talk to us about multiple stellar populations in globular clusters with James Webb Space Telescope. So Tuilia was a student here, an undergrad student in astrophysics here at URPIS, and now she's a final year PhD student in Padova, in Italy. She got her, and before that, she was a master's student at PUC, Chile. And from September, she'll be starting a postdoc at NOAA Lab in Tucson in the United States. So thank you so much, Tuilia, for coming and visiting us to present your current work. The floor is yours when you're ready.
Thank you, Anna, for the invitation. It's very nice to see you all here, so many familiar faces after all these years. So in the seminar, I'm going to be talking about my results with the JWST in the context of multiple stellar populations in globular clusters. So globular clusters. I still remember the first time that I heard about globular clusters around 10 years ago in the same institute. At that time, I thought globular clusters were kind of boring. I mean, they were just this spherical collection of stars orbiting our galaxy as satellites in the halo and in the poles. But soon after that, I found out that globular clusters are actually quite interesting. They are very, very old objects with ages of about even 13.5 gigayears. So we can even use them as a fossil record of the early universe in a field that we call galactic archaeology. They are also tracers of the Milky Way's formation history. So we can combine information of the chemistry of these clusters with kinematics to see if they were accreted from another galaxy, for example, or born in Milky Way. In stellar astrophysics, they are tracers of low metallicity synthetic processes. They are found in nearly all galaxies, so not only in the Milky Way, but even in high redshift objects. They can be used to constrain dark matter mass. They can even contain intermediate mass black holes. For example, this cluster in the image is Omega Centauri, and earlier this year, an intermediate mass black hole was found in its center. And we can even use it to validate the age of the universe. The problem is we still don't know how these clusters work. So until not very long ago, globular clusters were thought to be the best example of simple stellar populations, with all stars having the same ages and the same chemical composition. So if we look into some of the color magnitude diagrams that we could make with, for example, even HST, we could see this very narrow sequence that could be easily fitted by a simple cell population model. But nowadays, we know that using the right combination of filters, we can distinguish these different sequences that correspond to multiple stellar populations. So almost all clusters in the Milky Way contain 2 or even more stellar populations. A first stellar population, which are stars with chemical composition very similar to halo-filled stars of the same metallicity, and a second or even more stellar populations enhanced in helium, nitrogen, sodium, and depleted in carbon and oxygen. The tool that we use to study these multiple populations using photometry are these chromosome maps. So chromosome maps are these photometric diagrams made with filters that are sensitive to light element abundance variations and then can maximize the separation between the different populations in a cluster. So if a cluster doesn't have multiple populations, what we expect to see is something like what we see in the left here. So all stars near the origin with some spread because of photometric errors. But what we actually see is this picture that is a lot more complex. We have something around the origin here, but also different groups of stars that correspond to the second population stars. This is because of the different light element abundance that we have in these multiple populations. So for example, we have that helium is varying in this direction and nitrogen in this direction for this combination of filters. As I said, we still don't know how multiple populations form, but all the formation scenarios that we have can fit into one of these 2 categories. multiple episodes of star formation, or accretion of material onto pre-existing stars. So the first one, as the name says, predicts that the differences that we see in light element abundance content are because of multiple episodes of star formation inside the same cluster. So if you look into the chromosome map, you can see that around the origin, we have first population stars and here second population stars. And you may notice that there is something wrong with this scenario because the number of first population stars is a lot smaller than the number of second population stars. And we call this the mass budget problem. So in case this set of scenarios are correct, the solution for this problem would be that the cluster was a lot more massive at the time of its formation and lost most of its first generation stars to the galactic field. So as consequence of these scenarios, globular clusters would have contributed a lot to the formation of the galactic halo and possibly even to reionization. The second set of scenarios instead, that we call early accretion, predicts a single episode of star formation and that the chemical anomalies that we see are a result of accretion of material onto main sequence stars. However, as you may know, the amount of accreted material depends on stellar mass. Higher mass stars are going to create more material than low mass stars. So to test if this set of scenarios are correct, we could just measure the differences in chemistry between first and second population stars that are high mass and low mass. The problem is to do that for low mass stars in globular clusters that are located far away. So before the JWST, most of the results that we had, considering multiple populations in clusters, were made with HST or spectroscopy. But with the HST, we mainly use UV detectors, UV filters, to separate the multiple populations. And they have some limitations, so we can only use this for high mass stars, which are the brightest stars. And the same for spectroscopy, because of limitations in instrumentation, we can also only use it for high mass stars. And now with the JWST, we can successfully do this with the very low mass stars. This is because M-dwarf stars have a lot of these molecules containing oxygen in the infrared regime. So for example, here I show what we tested for a paper that I published on M92. So we know that second population stars are depleted in oxygen with respect to first population stars. So we can use these bands that are sensitive to these molecules containing oxygen to separate the populations among M-dwarfs. So in this context, M92 was the first globular cluster ever observed with JWST. It is a very old cluster with an age of 13 gigayears, and it's also very, very metal poor with metallicity of minus 2.3. So with JWST filters, we can make polar magnitude diagrams such as this one. And if you see here in the bottom of the main sequence, the spread that we have is a lot higher than the photometric errors, suggesting the presence of multiple populations. If we combine this information from JWST with HST, we can make these diagrams that are even more sensitive to some abundance variations, such as this one of oxygen and nitrogen, and this one of oxygen and helium. So we can combine these two diagrams to make a chromosome map, and then we see that there are three groups of stars in M92. We have one near the origin corresponding to first population stars, then these two other groups of stars that we call 2GA and 2GB. So if we consider, for example, a scenario where multiple populations are a product of multiple episodes of star formation, then this group of stars here that is close to this one in the origin would form very shortly after the first population was formed, and then we do have a third formation event that form this other separate group of stars. To get the abundance variations using photometry, what we did was to generate grids of synthetic spectra. We generated thousands of them and compare them with the observations. So we use the synthetic spectra to generate this synthetic photometry. Here you see different colors for the filters that we have in this work. And you can see the best fit that we have with the observations. Using this, then we get the oxygen abundance variations that are needed to reproduce the observations. Here you see 3 isochrones that are varying with oxygen, and all the other parameters are the same. And then the oxygen variations that we obtain in comparison to high mass stars in the RGB with spectroscopy and in the upper main sequence with HST photometry are consistent with each other, which is incompatible with the predictions from accretion scenarios. So the only scenario that can explain what we have for M92 are scenarios predicting multiple episodes of star formation. We did the same for 47 Tuc. So for 47 Tuc, we have JWST observations using both spectroscopy and photometry. So for the M2Rs of 47 Tuc, we got the first spectra ever obtained for M2Rs in a globular cluster. And then you can see also here in the color magnitude diagram that we have this sequence of objects below this point, which is about 0.11 solar masses. And here, these objects we think that are brown dwarfs even. So it would be the first detection of also brown dwarfs in the globular clusters. And this here is the Magellanic Cloud that was in the same field of view of the observation. So here you see in the upper panel the chromosome map with this other photometric diagram where we see a first population star in red and a second population star in blue. So we have for these two stars also the spectrum. We see that they are significantly different from each other, and from simulations, we think that this difference is because of this difference in oxygen that are present, these water molecules. So we did the same procedure using photometry. Then for M92, we also analyzed the spectra. And again, the variations that we obtain among first and second population stars are the same as for higher mass stars. So again, this is ruling out the accretion scenarios. So a summary so far, we can use JWST to successfully classify first and second population stars because of their differences in oxygen content. Then our results are inconsistent with accretion scenarios. And the only thing that we have left are scenarios predicting multiple episodes of star formation. But then if these scenarios are correct, we have the mass budget problem, predicting that globular clusters were a lot more massive during formation, lost their stars to the halo, and even have contributed to reionization. But how can we test if this scenario is actually correct? Like what we did before was to test if accretion scenarios could reproduce the observation. What about this other set of scenarios? We can test them by using multiple population kinematics. So if we have multiple episodes of star formation, we have first the formation of the first stellar population, which is extended. And then in the center of this system, we have the formation of second generation stars that are going to be more rapidly rotating than first generation stars, and of course, more centrally concentrated. And if we have clusters that are not dynamically old, these initial conditions of the cluster are still going to be present, and we can observe them in differences in some kinematic tracers, such as anisotropy, energy superpartition, rotation, and angular momentum, for example. So to explore this, what I did in my last two papers was to analyze the kinematics of two different clusters. We have 47 Tuc, which is the classical example of a type 1 globular cluster. Type 1 globular clusters are the most common clusters that we have in the Milky Way with this classical 1p and 2p separation. And we don't see significant differences in iron, for example, between the stars in this type of clusters. On the other hand, we have type 2 globular clusters, for which the most classical example is Omega Centauri. So in type 2 globular clusters, besides the classical 1D, 2D, because of different nitrogen here, you can see populations, you also have this radar sequence here corresponding to stars with different iron abundances. Depending on the cluster, we can also have C plus N plus O variations and S process variations in these clusters. So the question that I want to answer by using kinematics is that can we identify what are the different formation processes between type 1 and type 2 globular clusters? And also if it can fit the scenario where we have multiple episodes of star formation. So first, we analyzed 47 cup. For this cluster, we have some data sets with HST observations and JWST observations spanning about 25 years. So we can derive very precise proper motions for including the very low mass stars in this cluster. We also combine this data set with Gaia observations because the field of view of JWST and HST is very limited. So we could only cover an area from the center towards 4 half-life radius, while with Gaia we can reach 10 half-life radius. So here's just to illustrate how it's the data set. In the center with HST, we have these sequences here corresponding to the two populations of 47 Tuc with the chromosome map that I showed you before. And with the JWST, we also have this sequence that is larger than photometric errors, and we can also combine this with HST data to make chromosome maps to separate the populations. Then the first parameter that we analyze is anisotropy. Anisotropy is basically telling us if there is any preferential direction for the movement of stars in the cluster. It's defined as beta, and it's equal to 1 minus the square of the tangential velocity dispersion over the radial 1 squared. So if it is 0, it basically means that there is no preferential direction, the system is isotropic. If it is larger than 0, we have preferential radial orbits, and if it is smaller than 0, tangential anisotropy. So here are the results for the two populations. In the first column for 1G, on the second column for 2G, and then you have the comparison of the two in the third column. In the first line, you see the radial velocity dispersion, which is basically the same for the two populations. There are some differences maybe in the outskirts. For the tangential one, you see more significant differences, and this translates into different anisotropy profiles. So while first generation stars are mainly isotropic, we have second generation stars radially anisotropic. This is consistent with the scenario where we have second generation stars being formed more centrally concentrated, both from comparing this with simulations, but also with the idea that 2G are in the center, and then over time they tend to expand, so they have preferentially radial orbits. We also subdivided the populations into 2GA and 2GB, considering these subpopulations that we have in the chromosome maps. And then the kinematic differences between them are not significant. So we have basically the same profiles almost, and if we compare them with the 1G, which is isotropic, then we see differences, but we don't see differences between the subpopulations. So if they formed at different times, they were formed under very similar initial conditions. The other parameter that we explore is energy copartition. To understand energy copartition, we have to remember that the stars in the clusters are interacting, and globular clusters are very old systems. They are collisional systems. Doesn't mean that stars are actually colliding, but that they are interacting and exchanging energy. So if we wait long enough, and if we're talking about globular clusters, what we do have are very long time scales. The energy of the stars, the kinetic energy, starts to equalize, evolving towards a state that we call energy copartition. So if the kinetic energy is equal to a half times the mass times the square of the velocity, this means that high mass stars are going to move slower than high mass stars. To quantify the degree of equipartition, we use two models. The first one is the classical one, that says that basically velocity dispersion is proportional to the stellar mass time elevated to the minus eta, and we call eta the degree of energy partition. If eta is equal to 0, basically the velocity dispersion does not depend on stellar mass, so there's no equipartition. And if it is equal to 0.5, we say that the system is at full equipartition. The other set of models that we use is this one by Bianchini et al. 2016. It says that not only velocity dispersion depends on stellar mass, but also equipartition itself. So we have this parameter called equipartition mass. If the mass is larger than equipartition mass, it means that they are in equipartition. And if it is smaller, it is in partial equipartition. The challenge in measuring energy equipartition in globular clusters is that we need to have a very wide mass range, in the sense that if we consider stars in a polar magnitude diagram, for example, we see that RGB, HV, and HV stars, which are the brightest stars, comprise a very small mass range. So if we need to have wide enough mass ranges, we need to go to the main sequence. But it's very challenging to obtain good proper motion for the stars in globular clusters. So for example, with Gaia, we do have amazing proper motions, but only for bright stars. So what we did was to combine the data set from HST and JWST to derive these proper motions. And we obtained the masses by feeding isochrones from the Dartmouth Stellar Evolution database. So just so you have an idea about the mass range that we are talking about, we have in globular clusters, because they are super old, the higher mass stars that we have are of about 0.9 solar masses, and the smaller ones that we have from isochrone feeding is 0.12, but we can derive proper motions even for stars that are below that. So here, you can see the degree of energy equipartition in function of radius for the total velocity component, radial and tangential. The reason why I divided it to radial and tangential is because simulations predict that maybe the evolution towards energy equipartition is not an isotropic process. So you can see in blue the results for first generation and in purple for second generations. And you see that, for example, in the radial one, sometimes first generation stars have higher equipartition than second generation stars. But in the tangential ones, you have that second generation stars are always in more equipartition than first generation stars. So if you think about the scenario that we are trying to test, where you have second generation stars centrally concentrated, this makes sense with that scenario, because if they are centrally concentrated, they are interacting more and exchanging more energy than first generation stars. So we also trace the same model with this mu, which is equal to 1 over the equipartition mass, and we see similar results also for this model. So here we compare our results also with simulations from a work that I co-authored. We have the mu, which is this parameter here in the tangential component, for first generation stars in red, second generation stars in blue. Here you see 5 different models, all of them with different initial conditions, but all of them are with second generation stars more centrally concentrated. And you see that in the tangential direction, always second generation stars are presenting higher energy equipartition than first generation stars. In the radial component, we also see that we have these differences, like it's varying a lot with radius and also with the initial conditions of the stars between first and second population. So another parameter that we analyze that is kind of new in the context of globular clusters is skewness of the distribution of the proper motion. So here in the first panel, you have the skewness in the tangential proper motions, and in the second panel for the radial proper motions, you see that for the radial proper motions, skewness is basically consistent with 0, while for the tangential one, for first population stars, you see that it's a lot higher than second population stars. So we compared this with previous results in the literature. The only thing that we could find was in the context of galaxies using line of sight velocities. And in this case, skewness was a tracer of rotation. So this could imply that we have differences in rotation between first and second population stars, but we actually measured rotation and they don't have very significant differences. So we contacted some people doing simulations, and apparently one thing that can be driving skewness is mass loss processes in globular clusters. So if a cluster is preferentially losing, for example, first generation stars, the skewness would be higher for this population with respect to the second one. And this is more or less what we are seeing here. So this could mean that the cluster loses preferentially first generation stars. Then we analyzed also the kinematics of Omega Centauri, which is a type 2 globular cluster. Then we have for this cluster this area here for which we combine the JWST, which is in blue, with HST in pink, and also this one here at 2 half-life radius. To have proper motions also with a time baseline of about 25 years. So again, we have very good proper motions for this data set. So here in the right, you see also the color magnitude diagrams that we have with the JWST filters. And you see this sequence here and this other one here, which are kind of intercepting here. For Omega Centauri, it's not that simple to separate the stars in just 1G and 2G or 1G, 1P and 2P. We have the stars in the lower stream, in the upper stream, and in the middle stream. So basically, we have that nitrogen is varying in this direction. So lower stream stars are analogous to first population stars, and the upper streams are analogous to second populations. But we also have these populations varying with metallicity as well in all of the streams. So the first thing that I did was to analyze anisotropy among lower stream stars and the rest that I called upper stream stars. So it, again, very similar to 47 Cup, we see that the velocity dispersion profiles in the radial component are almost the same for the two populations. And then we see significant differences in the tangential component, translating into different anisotropy profiles. So we see that upper stream stars, which are analogous to second generation stars, have higher anisotropy than lower stream stars. So this could also mean that these stars are far more centrally concentrated than the lower stream stars. I also consider the two upper streams, so the one that is uppermost, which I call extreme, and the other one that is in the middle population, which I call intermediate. And then we see differences in their anisotropy profiles. So basically, we are seeing a gradient in anisotropy. We have lower stream stars, analogous to first population stars, being the ones more close to isotropy. Then we have the intermediary population, which presents also intermediate values of anisotropy, and the uppermost here, which is the most radially anisotropic. So this is suggesting also a gradient in the central concentrations of these stars. But if we subdivide the populations into metal-rich and metal-poor, then we don't see differences in kinematics. So this is suggesting that metal-rich and metal-poor stars that belong to the same population are forming the same subsystem. So there was that idea that maybe the differences in metallicity in Omega Centauri would be because there was another cluster that was accreted to Omega Centauri, and this doesn't make any sense in the context of analyzing kinematics. We do see some small differences among upper stream stars in the kinematics, but they are not significant. So basically, the conclusion is that they are sharing the same kinematics. Another parameter that we investigate is angular momentum, which is defined as the tangential velocity times the radius. We see in the upper panel the dispersion of this quantity, and in the panel in the bottom, the average of this quantity. anisotropy. And you see that lower stream stars present significantly higher angular momentum than upper stream stars. And the reason for that is mainly because of their differences in anisotropy. Because if you have radially anisotropic orbits, their angular momentum is going to be smaller than isotropic circular orbits. So if you are analyzing the dispersion, you are basically eliminating these higher values of angular momentum, and upper stream stars have, then the dispersion is going to be lower, of course. We also analyze skewness for Omega Centauri. So just by plotting the proper motion distributions, like the tangential against the radial, for lower stream and upper stream stars, we can see that lower stream stars are a lot more asymmetric than upper stream stars. And we can indeed see this. We have that skewness is consistent with 0 for upper stream stars, both in the tangential and in the radial direction. While for lower stream stars, we have significantly stronger skewness. So it could be the case that Omega Centauri is preferentially losing lower sequence stars, but more simulations are needed to actually investigate if this is what's driving the differences in skewness between the populations. We also measure energy diffraction for Omega Centauri, and we are comparing our measurements, which are the ones in the pink dots, with results from the literature. So we have that in the center, Omega Centauri is exhibiting higher skewness than in the outskirts. This again makes sense because in the center, stars are exchanging more energy and reaching equipartition faster than in the outskirts. So lower stream and upper stream stars are actually behaving very, very similarly to 1P and 2P stars. So probably this means that type 1 and type 2 globular clusters have very similar formation mechanisms. We also introduced some kinematic quantities that were unexplored in this context of multiple populations and globular clusters, for example, angular momentum and skewness, which are also showing us that there are differences in the kinematics between them. And considering Omega Centauri, if we divide the populations into intermediate and extreme and the lower stream, we see this gradient in anisotropy, which is also telling us something about the differences in the initial conditions of these populations. And our conclusion that metal-rich and metal-poor stars are behaving the same means that probably they were formed within the same subsystem. So in conclusion, for the bigger picture of globular cluster formation and evolution, what we did in this past 3 years after JWST was launched was to rule out accretion scenarios. So the only set of scenarios left that we have are the ones predicting multiple episodes of star formation. And then we have these consequences for the formation of the galactic halo as well, and also even for cosmic reionization. From our analysis of internal kinematics, we also can say something about the initial structure of these clusters. And our conclusion was that second generation stars are formed within a subsystem that is more centrally concentrated than the first one. Also comparing type 1 and type 2 globular clusters, we see that despite being very different clusters, they are sharing a lot of similarities between their populations, suggesting these common underlying physical mechanisms that occur in all cluster types. That's it. Thank you.
Question? Pablo?
Yes, multiple episodes of star formation, but the gas comes from where? From the stars themselves or accreted somewhere?
So in most of these scenarios, what we consider is that second population stars were formed from the gas that was directly accreted from the stars and then went to the center of the cluster. In the case of Omega Centauri, this is less straightforward because we have also this intermediate population. So there are some scenarios that we call, for example, dilution, where we have first the formation of the first population. Then we have the stars that are ejecting gas and forming the extreme population. And then Thirdly, we have another formation episode that is the result of gas that formed the first population stars that slowly went to the center of the cluster and mixed with the gas that was ejected by the second population. And then this is why we have this extreme population.
Yes, so the gas was always present in the globular cluster. Yes, there's no contribution from gas from outside.
Yeah, I saw that there are some models that consider that gas is still flowing, but most of them consider that the gas was ejected by the stars itself. Yeah.
So it's enriched gas. Okay, we have Hoyer, and then we have Horacio online. Go ahead. Can you please come over so we get the microphone in the YouTube recording?
So nice talk, Tuilia.
Thank you.
I was just wondering about the role of population 3 stars on your scenario. So what would be their role on setting the potential or the velocity dispersion of the older stellar populations that we see nowadays on these globular clusters?
So by population 3, you mean like those primordial stars?
Yes.
So they were probably formed before globular clusters, so they are not present at all in globular clusters. They probably enriched the medium before their formation. But interestingly, there are some studies studying metallicity variation between the first population stars in the clusters. So they see that population 1 stars are actually not chemically homogeneous as we thought. So they also have some metallicity variations like iron variations, and we think that this is because of the primordial gas. So I mean, for sure that the gas that formed the globular clusters was enriched by population 3.
Okay, now we have Horacio. You want to open up the microphone?
Hello? Hello?
Okay, can you
Did you hear
loud?
me?
No, we
Did you
can't.
hear me?
Try
Hello?
again.
Hello? Hello?
We can't hear you. Can you type your question?
Okay, thank you.
Okay, please type and then we come back. I have one question while Horacio types. Is how long what are the current simulations or can you tell from the data how long this process of first to second generation or population lasts?
So it's super hard to say this from the data, but from models, they typically consider that there's an interval of about 40 mega years between, like for sure smaller than 100. So for example, if you are repeating isochrones with differences in age, it
Doesn't matter.
yeah.
Go ahead.
Yeah.
Can you come closer back?
Very nice talk.
Thank you.
It's probably not the thing you're looking at because you're looking at very old stuff and low mass, but at this age, right, 14 million years, 40 million years, and a little bit older, AGB stars could be super important because they have a really long delay in ages. Like you get super HB stars, they are that form super young.
Yeah.
It could be similar to like the cloud formation, the time it takes for a star to form, and then you have more intermediate HB stars, and they have very different enrichment potential.
Yeah, so among all the scenarios that we have that fit into the multiple generation scenarios, we have the different polluters that were proposed to explain the multiple populations. One of them that is a very popular choice for explaining the formation of multiple populations is the one that uses AGB stars. So yes, for sure, maybe they were the responsibles for the second generation.
Yeah, and they can have differences in nitrogen and oxygen.
Yes.
In carbon 12 and 13 ratios, and even helium.
Yeah.
So it's a
it's a very good possibility.
Thank you. We have a question here from Horacio. Could the higher concentration of second generation stars means that they do not have enough time to be spread out due to two-body interactions?
Yes, for sure, because there are some clusters that we call dynamically old clusters, for example, M92, where we also analyze for several parameters such as anisotropy, and then we don't see any differences between first and second population stars. So we think that over time, because of two-body processes, we are gonna have also, I think that I didn't mention in my talk, but if we measure just like the fraction of 1p and 2p stars against the radius, we see that 2p stars are more concentrated still, but other clusters that are dynamically older don't have this concentration anymore. So, yes.
Okay, Charles?
Okay, if there's some contribution from outside gas, the bulge globular clusters should have more second generation stars. And are there any plans to observe some bulge GCs?
Yes, we have a paper coming out analyzing multiple populations also from the kinematic point of view in the bulge. And we recently also got a JWST proposal accepted. So we are gonna do a survey with the same thing that we did for 47 TET, Omega Centauri and M92 for a very wide sample of clusters in different environments in the
Are
galaxy.
there any systematic difference between bulge and the halo GCs? Some remarkable.
Actually, no, they are very similar in this like anisotropy profiles that we see. Of course, there are some exceptions, but
So
yeah,
the conclusion it's an internal mechanism.
yeah.
Yes.
Horacio wrote something else. Then the first generation could have been more concentratedly formed. I think
I
that,
don't guess what you mean.
Nicholas, you had a question, but the microphone doesn't work. Do you want to type? He's typing. Oh, I don't know if you like. Do you have more questions from the audience? We have some time. So I have a few last ones. So with the main thing you learned, you gained with James Webb would be the depth. And what the new facilities that are coming out, including LSST and the Chinese one, the CSST, what do you think, how much they will contribute to the advancements in this field of globular clusters? In what senses?
So considering this analysis of multiple populations, the LSST doesn't have the proper filters for separating the multiple populations. But it can be used, for example, for the outskirts, because some clusters could be losing stars. So we could maybe look for low surface brightness features around globular clusters. Regarding proper motions, also the LSST is not super good for the cluster centers because of resolution issues. So maybe it could be used for the outskirts, but at the same time, we also have Gaia and other instruments, so I think it.
But the
would
U
not be
band
very
is not good enough? The U band is not good for separating.
So what we usually do using like ground-based facilities using the U, B, and I filters, the LSST doesn't have the B. So maybe we can
G.
make some tests with G. I think someone already did in my group and it was not very good for separating them.
Yeah, just a comment, LSST will have proper motions over its 10-year baseline.
Yeah.
Which will amount to 1 milliard second per year for a 24th magnitude star in our band. So that's much fainter than Gaia.
That's
Actually,
very good. Yeah,
Of
so,
course, you'll be able to measure these, as long as you resolve the stars, so you will be able
Yeah.
to do that on the outskirts, not.
yeah, yeah, outskirts, it would be
It
great.
certainly complements Gaia after
Mhm.
10 years, the observations towards stranger magnitudes.
Mhm.
Reasonable decisions.
Yeah, good point.
And as for the filters, we have done tests and they do separate, especially for the bright stars, the UV.
Oh, that's
Yeah,
great.
it does.
Yeah, so it would be good, for example, Palomar 5, for example, is a cluster that has this very extended tail. So maybe we can use this combination of filters to separate them into populations and actually see if the cluster is losing preferentially first population stars. Yeah.
Because it's super nice to go super deep, but you get just pieces of the cluster. It would be really, really great to have a
Yes, for sure.
wide field of view and homogeneous.
Mm-hmm.
But this field is constantly evolving. Yeah,
Yeah,
there's,
for
lots
sure.
of bits of it.
Yeah.
So let's get Nicholas's last question, which I have to read. You mentioned simulations models when talking about kinematics. Are those in-body simulations? If so, which software is used for those simulations? Very specific. Not
so-
observational that you did so.
Yeah, I didn't write the simulations. I know that they are n-body simulations, and you can check the simulations from Vesperini, his simulations, and you're gonna find all of the details.
Modest. You can check the Modest
Yeah.
page.
Yes, for sure.
Okay, so if there are no further questions, let's thank you.
Thank you.
And we can go further
Invitation.
talking.
Also, ich habe auch
Peraí, eu vou me-
Isso
Ah, aliás, isso é porque